Hello everyone, it is Alimzhan, uh, pronouncing my name like a foreigner. It's Alimzhan, Amanov, and that is the Algorithms in Data Structures lecture 3, like week 3 lecture. This is actually a second lecture, assuming that the first lecture was the lecture number 0, introduction. Okay, so today we're gonna have a linked list and double linked list, which is two very basic data structures that they're quite abstract, um, but we will see how they are constructed. So what is linked list? So here is a diagram of a linked list. Linked list is a sequential collection of nodes. So it's a bunch of nodes. This is node, this is node, this is node, and each node storing information, um, two things. It's storing information in two things, like a data, some arbitrary data. In our example, it would be an integer. And what else it stores? It stores the pointer to the next node. All right. So we have initial node, we have a pointer to the next node, we have a pointer next node, and so on until we reach the end. So the end points to null, to nowhere. Okay. As soon as we get to, as soon as next is null, we know that this is the tail. This is usually called a tail of, uh, so this is called head. Oh, this is too bright. This is called head. So this is the head, and this is the tail of a linked list. So the difference, so double linked list is the same data structure, almost the same, but we have additional information here, which is the link to the previous element. So as in the linked list, each node contains data next. So data is some data which we are storing, and next is a pointer to the next one, and also we have a pointer to the previous one. So head would have previous equal to null, and the tail would have next equal to null. So here it must be next. So what's the main difference? So what's the special about this data structure? It's actually very limited, and it cannot do many things. I mean, if, at least effectively, as effectively as others does. But the concept itself is natural and um, at- like we should be aware of it, and we should know how to handle it. Okay, so in array, what you can do, you can access the ith element, right? So you can access the ith element instantly in big O of one memory. So it's like a constant, it's a immediate operation, right? So what it basically does, it takes the zero element. So array, as you know, as you remember, is the, for example, in C++, it is a chunk of memory, all right? It's a chunk of memory um, stored sequentially in the memory. And what you can do, you can take the how you can take the ith element instantly. You always have this a as an index to the zero element. So this is the zero element. So this is actually a pointer to the memory where zero element is stored. And then what you do, you just move your iterator forward to I positions, and you obtain the ith element of an array. All right. So this is how it happens in the arrays. But our concern would be how long it takes, and this is like a trivial example of trade-offs we have usually in the data structures. How long it takes to, for example, get some element which is equal to x, how fast it is to insert an element, and so on and so forth. So we are going to be interested in three kind of operations. Let me draw it like here. So yeah, actually, um, here let me first briefly remind this. So this is the basic um, declarations, what we have in the linked list. So this is the list. So linked list, it should probably be linked list, not list, like a linked list. All right. And what we're gonna have here, we're gonna have a pointer to the head. So in case of singly linked list, it is just a head. In case of doubly linked list, we also can have a tail. Okay, and what the node contains, so this is the pointer to the first element of the list, so like to the head, and sequentially then we can access the further ones. But what we store in a single node, we store a data. In our example, it would be just an integer, just for simplicity. But actually, you can store anything else here as well. So, and what else we have? We have next. We have a pointer to the next element and pointer to the previous element. So be aware of that. We're gonna use a pointers in a few lectures, so you should actually better to be prepared for that. So maybe you should train yourself in pointers and so on. So maybe you should teach what pointer is exactly, which would be very useful for you. Um, okay, so we are going to be interested in three kind of operations. So first of all, it is so what we're going to do, what we should know about it is how to insert, let's say A to end, B to the beginning, to the beginning, maybe there here as well, beginning. I'm not sure if it's double end, doesn't matter. Okay, and just uh, random insert. Random means it's not like a is equiprobably random. It means like just in any place, random insert. You should know how to insert in any like in ith position. Let's say not random. Let's say specific position at pos I. So after the ith element or before the ith element, so that inserted element would become element with position I. This is usually what's called insert to the position to the position I. Okay. Um, what else we're gonna be interested in? So this is the insert. Uh, maybe we should know how to get. So get uh, pos I element. So get element at position I. Maybe we should find element, find X in the list. What else should we want? Um, and of course delete. So delete, get, insert. This is like a very basic stuff. So delete maybe first X. Okay. So there are a bunch of interesting problems for the linked list. In fact, um, like a range of there are a range of problems that based on the linked list that usually people ask on the interview, like two turtles problem, like a find the period of a linked list. If you know that the tail is linking to something in your list and so on. So like quite interesting problems. Okay, so before that, like if you were wondering where it appears and so on, um, this is actually um, it is actually what happens frequent, like it is underlying structure um, in many things. Like for example, the comments in the social networks, they're built up like so each new comment is actually referring to some comments, right? Usually it is like this, maybe then someone replying to this comment and so on. So each new comment is replying to another comment, yet another comment is actually storing a pointer to who he or she is replying to. Okay, so I have this guy have a pointer to this line. This line have a pointer to this line. So this is basically a linked list. But this linked list is not like this is like if you start from one to the top one, um, then this is a linked list, but actually it is like a directed tree or so. So, for example, this situation also may happen. Then this is not particularly linked list, but the single pass is the linked list. So, and lots of example like this. So you usually need to store, you like graphically represent it like this, but you usually need to store it um, in database, and the format which is storing in the database is actually a linked list. So yeah, funny thing that quite recently, the friend of mine were having an interview to some gaming company, like the cool one, and what they asked for is the following problem. Let me briefly like explain it to you so that you will be uh, so would have motivation for really studying this subject. Okay, so the problem was you're given the list, uh, you need to serialize it. Oh, no, no, no. You are given the list in the format like, um, not, okay, list is in format head and so on, but you're given the nodes, each node having like some integer in data. It has it was actually a string, but it doesn't matter. Is it a string or is it something else? Okay, it's string s, some string, and some uh, pointer to the node next. And actually, it also contains pointer to some random elements. So some random elements uh, of the list. So you see, like list could be like this, and also uh, each node contains some additional link to some random element. This could be like this, uh, like like this. This can point nowhere, so now, and this can point to like, for example, this again. Okay, or maybe lambda, or maybe this, for example. So this is can be random even now. And so you need to restore this list, this tricky list, with full information. So you need to first, so you are given the list with these random links, additional random links. So linked list, all right? Okay, like the RL, like a random linked list. Okay, or linked list with random. Okay, you need to write it into the file. So it is this process is called serialize, serialize, serialize. And then you need to you need to be able to deserialize it. Deserialize it. You need to, let's say this is X, and you should get X. So you need to deserialize it so that you obtain X back. So the problem that you may think that it is easy, but actually this is quite a tricky one because you cannot, you don't have an index, right? Oh yeah, and your asymptotics, so the requirement was that the asymptotics must be less than big O of n square. So it should not be quadratic, i.e. in essence, this should not quadratic, not quadratic. And it's actually easy to fall into this trap. So first thing that my friend did is an n square like solution, which was correct, but um, not um, как это, liable. But not liable to uh, like what it wasn't. It was correctly working, but it wasn't what did match the requirements of the problem given to him. Okay, so yes, this is interesting problem. This is like an exercise. This is your job interview. Let us think that we have a job interview as your exercise. If you succeed with that, I will send you a link where to apply. Interview, job interview. Okay, and you need to be careful with those tricky cases that we would have. All right, so any questions? Of course, you cannot ask a question, but we will have your questions at the lecture. So this is the short explanation, or not short, of what is linked list is. And so this is quite simple, quite obvious, but the tricky part, the most hard part in this chapter is the implementation. So it's not actually that hard, but it may cause you some problems. Okay, let me transfer to my working space. All right, so let's jump into implementation. So we're gonna have here a node. Oh, let me swap their positions actually. This is important. Okay, we have a node head. So we're gonna start with a simple linked list, and here we're gonna have a methods like, for example, int get and int position. All right. But first, I'm gonna define what is node. Node is simply we're gonna have pointer to next, and we're gonna have a data. All right. So this is the data, this is the pointer to the next element, and that is everything what we need. So we can set it initially to the null. I believe that modern compilers are um, are casting 0 to the null as well. Let us try this out. Let me create a node. So the way we create a node, like current for example, or n, is the operator new, which what it does, it dedicates the memory, required memory for the pointer. Okay, so now the pointer actually points. So if I create it like this, so this is just be a pointer to nowhere. It doesn't have any address. But and now I am assigning a memory to that pointer, so that now it points to some memory, and now I can set some values to it. Okay, and data. Let me assert there is some function assert that asserts something is equal to something. Let me try this out. And next equals 0. This is not the proper way of doing that, but maybe it is. So okay, let me make it larger. Yeah, let me make it larger. So let us start it. Yeah, that works. So this is actually 0, and let us try null here. Yeah, that works too. So yeah, we can just say this as 0. So, but basically, what we mean it is null. Null is some um, special object, special like value of the pointer that says that this pointer points nowhere. Okay. Okay. So, well, we'll write 0 instead of it, just for simplicity, and this way our code would look more natural. Okay. So we are done with the setting up. This is the way we create nodes, and now let us, okay, before we can get something, we should be able to insert the list. Okay, so no, void insert, point, this function returns nothing, but what we can insert x and insert, let us start from insert begin. All right, so this is the way we're gonna insert into the beginning. So which is like we have a linked list like this, 0, null. So if I want to insert it, what I can do is to just create a new element. I'm creating a new element, new element, and just point it to the head, to the current head, and just say that the linked list that the heads just have been updated. Okay, so what I'm gonna do, I'm gonna create a new node. So node, uh, new node, which is new node with the value x. So I can actually create um, create the constructors which are going to the good way of doing that is like this. Alternatively, you can write it like this. Let me just show you, but I'm not going to use that because sometimes people tend to say that this is unreadable, like this, or even I can do this. Okay, so what it means, let me return it to this state so that we can differ two variables. So what it does, it just when we write here two dots, we mean that we're gonna use inherited, or might be not, yeah, inherited. So we're gonna use like constructors that are already um, defined in the components of our structure. Okay, for example, integer have a constructor with that sets the integer. So what I'm doing, I'm accepting in my constructor of the node, I'm accepting the data um, data integer like underscore data integer, and I'm passing like I'm saying that the object like the integer data must be initialized with the input with this inputted integer must be initialized with this inputted integer. So this is one way of doing that. Another way is like that. All right. So this context, it usually doesn't matter how you do that. Just this is like reducing the code you're writing and reusing the code that were written in this constructor. Okay. So the way I'm gonna insert it, I already described it. So okay, I created a node. What I should do next? Of course, I'm doing the following. I'm already set up what should be there, and now I'm setting up what should be next. And I'm gonna set. I even can actually do this. I can create a node like this. Nodes next. So like those three are basic constructors for our nodes. Like those are natural ones. So maybe we may want this to have place. Okay, so like I writing next equals next. That's it. So now I'm instead of writing this line all the time, I just can initialize it with what's required. Okay, after I created the node, I already said what it should point to, and I just want to say head equals new node. That's it. All right. Of course, instead of this, you can always write it like just create an empty node and then set data to x and head to x and so on. Let us write actual data here so that it would make sense more. Okay, this is the simple one, insertion into the beginning. Let us now see how insertion looks like when we're trying to add it to the tail. And then we're gonna deal with and then we're gonna figure out how to insert it somewhere in the middle. Okay, I'm gonna insert the tail. I'm gonna insert it to the tail. So what should I do? I should create the iterator head. Um, I should obtain the tail of our linked list. So actually, what I might consider to do, maybe that would be reused everywhere. Actually, I should better to write it like with this style since I started already. Okay, get tail. I should maybe uh, create the function which gets the tail. So how am I gonna do that? I just go while head is not null. So if head is null, head equals null, then return null. So return 0, all right? And otherwise, if head is not null, I'm just going until head is not null. Okay, 0, right? And I'm gonna if it's not 0, then I do the transition and again ask if it's 0. If it's not 0, and I do the transition, and of course this while will end up uh, while whenever head hits the tail, because the tail is the only guy who has next as a null. So I should return head here. Oh no. Sorry. I should create a new variable for that actually, because I'm here and I should not alter this head. I should not alter this head. Okay, that's it. So current equals head, current next. We do the transition. If it's not null, then I can do transition. I do transition until I can. So okay, coming back to insert tail. So what I can do, I can just get the tail. I got the tail. Now I should create the new node. New node with the parameters, the specified data, and it is going to be a tail, so I should put here a null. Okay. And now I should say to the tail that you're gonna continue not to the null now, but to the new node we've just created. That's it. We ended up we've done with insert tail. And now finally let us try to insert just to clear insert in data int pose. What we're inserting and where should we insert it. So let me specify what does that mean. Let us say I, for example. So what does that mean? We're gonna insert at pose I means uh, put element with data at position I, moving um, everything to right. So I wanna my new element end up at position I in the new list, so that the other guys who were starting from, so what was before starting from position I and further, we will shift to the right, like an array, like in an array. But what happens here, we actually don't need to do that, like um, we don't need to specifically do um, do shift, all right? So what we can do, let me draw this for you. So what we can do, so how insert should like, so insert will look like this. So we have an array, and let's say somewhere, so this guy is at position I, okay? So this is the current position I. Maybe I should draw it like this. So this is the pos I element. So this is ith element. So this is 0th, this is first, and so on. This is ith element. Okay. What I can do, I could say I could find the I minus first element. All right. And now just redraw this local picture to the following. I can just change it. This is still I minus 1th element. This is untouched. Okay. And then I just adding a new element. This is our new element. And then from this element, I'm pointing back to the previously ith element, to the previous ith element. Okay, let's us if I just gonna call it like A and B, I'm gonna say here A and B. Okay, so we just removing this connection. So this was connected before. I just remove this connection. I remove it and I add these two. And I add these two. Okay, this is the way we do the insert in the beginning. According to this picture, what should I do first? Um, what should I do first? I should get the I minus first element and then try to insert it. But before I should write the get I minus one element, I minus one elements, get like node ith I minus one elements. It's I minus one, like node A. Okay, if we believe in the picture, this is the node A. This is going to be a node A. Node B is going to be the next of the A, and just we're gonna create a new node. This is not the best naming actually, but we're gonna stick with that. New node. We're gonna create a new node with the data, and the next element of this new data is going to be B. And just we need not to forget to say that the next guy is going to be a new node. Like next guy from the A is going to be new node. So this is the link from new to B, like new to B, and this is the link from A to new. This is the link from A to new. So here we're just rewriting the previous connection between A and B. Okay, first we should implement get, and then there's one thing. Uh, let me just say it to do. To do corner cases. We're gonna have to consider corner cases as well. So, but before that, I should implement get. So I already have get tail. What I'm gonna have now, what I'm gonna have now is get element at position I. Let us say that this is gonna return element, like return node at pos I, or return null. Okay, that way we're gonna be safe. So I'm just gonna iterate for j from 0 to I. I'm gonna iterate j times I times, and I'm gonna try to do the following. I'm start from the head. I do the transition car equals car next until I get the next element, right? And then return current. Here we should be careful, because every time we access the node, every time we're gonna access the pointer, we need to be sure of if it's initialized, if it's alive, if it's not null. Because if you try to access the pointer, like this operation means go to the memory, take the value I require, like go to the memory which car points to, and take like the next, or take the data. In our case, it's only two. But if it's null, you're gonna try to do that, this gonna end up with unexpected behavior, in your program either would crash, which is like most of the times it just crashes without any troubleshooting. uh, for example, in Java, this is very good. This will show the traceback, and you'll show where it is actually trying to access it. But in C++, which is like a great thing and a bad thing in both cases, like this is just some trade-off I'm going to speak of further. So in C++, you don't have such troubleshooting. And that is going to be our main pain. But it's actually good for training, since you should be able always know where this error comes from, and that will train you better. Okay, so car next is not can be not initialized. In which case it is not initialized in the case when we went from current to the next to the tail. Uh, yes, when we moved from um, yes, from null to the tail. When we moved from tail to the next element, and we ended up in the null. So we should check this. If it's null, then I'm gonna return null, because in that case, if I just jump over, I mean, if I did reach null elements. I did reach end of the list before this loop ended. That means that I have elements. So someone asked us to insert some elements like to the non-existent position, right? And in that case, we're gonna return null. And in that case, so and then after this for, if this for completed successfully, then it means that our element would be current. So in worst case scenario, it's gonna return null. It's gonna return null here. If it return null here, that means that we finished at the end of a list, and if it returns zero, we finished at oh, if it again returns null here, it will mean that I is out of a reach. In both cases, what we're gonna do, remember I told you here that there are corner cases. So what happens if A is null here? So this is the corner case we're talking about. So what happens if A is null here? And it's not hard to understand that in that case, we should return, if A equals 0, we should try insert it into the tail. So in any case, we're going to insert it into the tail. So if our list have size 3, for example, and we are told to insert it at position 5, like let us say that this is our feature that we're going to insert at the ith position. It's like at the tail. And actually, in the case if we were told to insert it at position 4, um, if we were told to insert element at position 4, if lists have a size 3, this means that it's just append to the tail. Like this is natural thing to do. Um, this is like usually means that. Okay, and if I'm not mistaken, um, we're gonna actually ask me about it during the lecture. Um, what is best practice in here? So what usually other data structures do when they're requested to insert the element at position that does not exist, or a further of the length of the array or of container. Okay, so we're done here. Insert is now working properly. We actually should, we wrote down tons of code, so we should actually check this out. So let us try linked list. So we create a linked list L, and then we're gonna just insert position 0, insert element 1 at position. We actually should swap these things. Usually insert position and then the element. Yes, everything other is fine. Insert position 0, uh, let's say 1. Insert position 1, 2. Insert position 2. Like let's say 10, 20, 30, 40. 1, 0, 1, 2, 3. And let us write, we already implemented get here, so we don't need that. We don't need that. And then let us implement like a function output, which is gonna output linked list. Oh, one more thing. Um, the thing is, how you remember that we only have head here, right? But our head nowhere initialized in the insert. So in case I'm gonna create whenever I'm gonna try this, the head is not gonna be touched, right? So we actually need to say that if I equals 0, uh, insert begin data and just return. So that's it. So in that case, when we're gonna call insert begin, we're gonna create a new node and set head to the new node. So we're gonna initialize the head in that case. Okay, and now it's perfectly fine. So we're gonna let us implement like function output, which gonna output our list. I actually would be glad to show you how to make it so that it's gonna be outputted using the cout. So I'm just gonna write. So I'm gonna show you a little bit further how to make it work like this. Okay, cout. Um, I'm gonna iterate over the list. So while uh, node current equals head, while current is not 0, I'm just gonna return cout current data. Oh, sorry, current data. Um, Let us actually do this. If current next equals 0, then cout this, else cout comma and space, and then do the transition, or maybe like this. So what it does, it just outputs data, and then if we are already reached the end of our linked list, we're gonna say okay, cout, like we're gonna close the list. Otherwise, we're gonna put the comma. Okay, and let us try this out. L output. Of course, nobody expected this to work from the start. Okay. Okay, now pause the video and find an error. I'm gonna slowly, I'm gonna slowly scroll it down. And now, at any moment, pause the video and try to find the error. Uh, why it breaks. This is gonna be great. This is gonna be a great exercise. Okay. Okay, guys, I found the problem. There are two bugs actually. The first one is that whenever we're trying to insert this, like whenever you remember I told you that when this get fails to obtain like existing elements, so if a equals 0, then we are insert into the tail. But we actually should end at this, same as we end here. So this was a problem because now we're trying to insert several elements. So it's gonna insert the element twice. But that is not the problem that caused the segmentation fault. So you see this this is what happens when you're uncareful, if you're careless about the pointers. So actually the problem was, guess what? This. So we need to initialize it with the head equals 0. Now it's gonna work. Uh, Maybe I should add end of line here. Yeah, now it works. The problem here is that So this is actually a very deep bug. I mean, in terms of our program. So if that is not the case, let us see what happens. This is ability that you should obtain in order to find those bugs. For example, if I try to insert whenever actually the problem was that is this output function does not does not have an end, because here the condition for the end it is that it is equal to null, right? If current at one point at some point of time equals to null, then we stop this program, stop this function, right? So we stop this while loop. But that didn't reach its end because current in this situation appeared to be something different than null and some memory. This happens here as well. In exact moment of that, so as you can see here, we always insert to the end, to the tail maybe. Yes. So the problem was here actually. Insert before, not here, insert tail. So initially head is not null and not something. We create some tail and say that oh no, actually it is here. So whenever we say that new node has the pointer next head, and head has a pointer new node. So at some point of time, this head is transferred, and like so we just move this. So wait a second. Insert 0, we're gonna insert to the beginning, right? Insert 1, we're gonna insert to the tail. We're gonna insert tail here. Oh no, we're gonna insert here. Oh yeah, that's it. So initially we're gonna do this, which is actually the same as this. So we're gonna just here move B is the pointer, is going to be the pointer from head to next. It's going to be the pointer to somewhere else, which is not a null. So initially it's gonna, okay, initially when this line comes into play, this function is called because I equals 0. Then we create a new node which points to, let us call it strange location. Okay, this strange location is now um, where tail points. So the only element points, because initially we have only one element. Then we insert that to the tail again, but not via this one, because get I minus 1 will get us actual tail of our list. So this is always going to be a tail of our list in this example. Okay, so we're gonna insert it to the tail. So we're not gonna do this, we're gonna do this. And this, what it says, it takes B, the next element of A, which is tail, and next element of tail, as we already mentioned, is again this strange position, and this strange address is propagated to the next element, and so on and so on. And that is why we ended up with a tail which has pointer not which has the next pointer next, not to the null, but to the strange position. This is weird stuff, but this is what we gonna face in the C++, and that is actually funny thing about it, because we can spend few hours on it, and that would be a stupid bug. So be careful always with it, because such kind of problems actually will cause to some memory leakage and so on, and some memory flows and or data flows and so on. So memory flow, it is when so for example, here we create a pointer to the to the node, and what is memory leakage is when we created the memory having some pointer to it, and then at some moment of time we remove, like maybe we just we reassign the pointer to something else, but this data still occupies some memory in our storage, but no pointer accesses it. And that is the reason that is called memory leakage, because this memory, nobody knows that this memory is not like nobody is pointing to it. There are tools called garbage collector in some programming languages like Java, for example, and maybe modern C++. I don't really know about that as well, about about that for sure. But there is a thing like no, so C++ does not have this feature, and I know reason why. So C++ does not have garbage collector because okay, there is a reason for that, but mm, that is why you should be always aware of a memory. So we're gonna do delete operations as your task. And what you should do, I'm gonna write you like a simple delete operations, um, like delete tail, delete end, delete tail, and delete begin, and you should be able to do the rest. So let us try to insert now, not to the end, but somewhere in the middle. Let us insert at position 250. Then this should end up, so the result would be 10, 20. Now position 2 is 50, 50, 30, 40. This is 10. This is 10, 20. This is 20, 30, 10, 20, 30. This is 30, 30, 40. Yes, like this. Let us try this out. I hope it's gonna work. Yes, it is. Okay, so maybe we should try some get operations, like cout, get position, let's say for data. Oh my god, I hate this keyboard. Okay. Oh, get. Of course, get should be of our L 40. Yeah, this is the indexation is from 0 here. That's it. Now let us implement delete. Oh, uh, okay. This is color ratio. I hope this is not gonna. Yeah, delete is reserved word, so we should not write delete. Let us write it del, just del. Del begin, del end, and just del int I at some position. So del begin, what we should do, we're gonna say, we're gonna remember alt head, big alt head. So we're gonna remember what is the alt head, and we're gonna propagate our head to the next element. So that next is yeah, we should actually, as I told you, if I access here a head, so I should verify that it is not null. If it's null, I'm gonna do nothing. Okay, so this is pointless operation. So I'm gonna remember what is alt head, and I'm gonna propagate the head. And now, as soon as, so this is what happens. So this is just picturesquely, we're gonna have this. This is the new head. This is the old head. I'm gonna just remove it. Just remove this and declare this as the new head. So, but initially, old head is the old head. So yeah, propagate it. I say that old head should now be deleted. Just to say that to forget the memory. So no memory leakage, memory flow leakage, утечка. No memory leakage here. Same ways, delete begin. Delete end. So what should I do? Now, yeah, I just can get the tail. No. I should get the element before the tail. Okay, I should get the element before the tail because I'm gonna say to the element before the tail that you are no longer pointing to somewhere. Because let me just show you. Because if I just try to delete the tail here, the problem is that the guy who is pointing, if I'm just gonna delete this guy, like a, like a delete, boom. This guy is not necessarily pointing to the null. Like we should be always keep tracking of it. So let us assert. Now I get another tail. Asserts that its next equals 0. If it's not, then we're doomed. We should do something else. Let me try to delete end, l delete end. Let us check. Okay, let us check first l.output, l delete begin. Alt head was not declared, of course not. It was not. Yeah, some problems occurred. So what happened here? Okay, this guy is no longer needed. So I deleted begin. Let me like output it step by step. So yeah, I deleted the end. I deleted begin. So this works like a charm, as they usually say. And now I try to delete end, and it fails. But this assert still work. Interesting. I try to delete tail here. What happens? Who is this guy? Oh yeah, maybe yes. Maybe this is actually the reason why it happened. So you see here, this is unexpected behavior. Here you see this is a different number now. Just because this is like unexpected behavior, nobody knows. So you see this is each time different numbers, since just because the guy before the tail still points to this section of the memory, to this memory, still points to the memory of the um, like a former tail memory. But now it is not, but he still thinks that this is there, but something else might be there. And now we're in trouble. So we should do that in a different way. We should take the guy before the tail. We should somehow know he is a tail. So this is how we're gonna do that. So in case if head of next is equal to 0, then we just need to delete head and say that it is 0. Delete head. So head is a tail. Head is a tail. So one element case. So in case head is 0, then we just return. This is the same thing. Empty list. Head is a tail. We should delete the tail. We should delete head to say that head is now null. And exit the program. And exit the program. Now, if head, now there are at least 2 elements in our array. Okay, so what we can say, we can do the following. We can find the guy before the tail. This is the safest option. While head next equals 0. I'm sorry, not current. So we create the iterator, and now we say that if current of next is 0, so like so who is the guy who is before the tail? Is the guy whose next is 0, is null, right? Whose next guy is a tail. So until this happens, until this is not happening, I say that car equals car next, current equals current next. I do the transition. Yes, and now I'm safe to do this. I should delete my friend tail, my tail friend who is next to me, and say that um, and forget about him forever. Say that he is null, he's zero. Uh, Search guy before the tail. Now it works. So this is an exercise to you to implement how to do the delete functions. Moreover, there are there are additional problems in the lead code, which are of a which are quite interesting. For example, the first example is you are given already two list nodes or two linked lists, and you need to just append one to another. So we already know how to do that, but you need to complete these functions. This is the one example. What else? Remove one linked list elements. This is exactly what I'm asking you to do. Yeah, you should just delete arbitrary element of the array. Oh no. Yeah, you should remove all the sixes, for example. So this is the multiple delete. And that is actually a tricky one because you should be always. Oh yeah, final thing about yeah, you should be able to do that within. Um, I'm not sure if n square complexity would pass this, but I doubt it. So I think you should better to implement it in linear time. So the algorithm here is to go from left to right and land and see if the next element matches this matches this equality. Then I say that okay, I'm gonna remove them. I'm gonna remove him. I'm gonna say that the next element of him is my new next element and delete him. That's it. So yeah. So here are very nice problems on linked lists, which each of them, so the lead code is the website that actually designed for the interview questions and like just exploring the different problems in programming. So there are lots of interesting problems here. Like like when you see the solution, you say, "Wow." Okay, so and one more thing I want to talk to you about is the asymptotics of this algorithm of these operations. Let me. I'm gonna post it into the GitHub so that you can complete this implementation with this function. Okay, and what I want you to do uh, is to think of what's the complexity of all these operations. What's the complexity? So assuming, so what's the complexity? So complexity, let's say complexity. So complexity of these algorithms, complexity, uh, time complexity, to be specific. So we assume that number of elements equals to n in our list. So in order to do this, for example, to append to the end, what we do, we pass through entire list once, right? So we pass through each element once, and then we reach to the end, and then we append it there. So this costs big O of n time, right? Because we touch each element of our list once, and then only we append it to the end. The beginning, to append to the beginning, this is big O of 1 time, which is called constant time. constant. This is called linear time. And insert at position I is again linear time, because so big O means worst case scenario, right? And worst case scenario, position I could be the ends, and we know that this is big O of n, even if it's half of it. Big O of n over 2 is again big O of n. That is the same. So, so multiple of, like constant multiple of our n is again big O of n. So n multiplies by some constant is again big O of n. So get position of I is of course again by the same means linear time. And let us say that these guys are the question for you. This like trivial answers, but I'm gonna ask you while our meeting. Okay, so this is everything uh, about linked list. So yeah, I didn't mention you about double linked list, but actually this is almost the same, but it's just a bit more code because but more flexibility because because we always have a previous element. So for example, when we implement delete, we don't need to find the guy before the tail. We can take even delete end. We don't need to guy before the tail. We can find the guy who is. We can find the tail and just get the pref of it, right? Which is will not affect our complexity. This is just one extra step we did to find the tail, and then we come back in the constant time, like with the pref link pointer, if I would be more precise. Okay, um, that's pretty much it. If you have any questions, please prepare it to our uh, lecture time at Monday. All right. Um, yeah, please prepare it, and if you have any suggestions about how to record it and so on, uh, you're welcome. Okay, everybody, see you on the Monday.